Okay, welcome to Unit 4. So this is called Relations and Functions. We're going to start getting into graphs and Cartesian planes. Today is our first lesson, so that means you're watching this flipped classroom at home, and then you'll be able to come to class and practice your skills in class rather than practicing at home all the time. Let's get started. So the first thing is going to be a little bit of review. Now notice over here on the right, we have what we call a Cartesian plane, or what most people refer to as just a graph. We have a plotted of points over there. You'll see there's a whole bunch of them. And the first question here is to complete the following by writing the coordinates of the points represented by the letters of the grid. So they're saying, what is the location of point A? So you come over to your grid, you find point A, it's over here. To figure out where it is on the grid, how to describe it, so how to find the coordinates for it, you always start at your origin, which is the very center, and you're going to count however many steps to the left or right you need to get so that you're right above or below the point. So I have to take 1, 2 steps to the right to be right below the point. I'm not on point A yet, I'm just below it. That 2 steps to the right, that's your first thing that you put in the coordinate. It's also called your x value. So your x value is your first point in the coordinate. You then have to go up or down to get to the point, and you count your steps. So 1, 2, 3, 4 steps up means that the second value I put in is 4. And notice that I write it in as x, comma, 4. Or x, comma, y, 2, comma, 4. That's how we always list coordinates. So that'll always be the pattern we do. Now I know some of you can do this a little faster. You can look at points and you can figure out where they are. But this is a foolproof method. So the next point we're going to look for is B. It's over here. We're going to start at the origin. We're going to do left to right first to see how far away we are. We have to go left, 1, 2, 3. When you go left on a graph, we represent it with a negative sign. So we went -3 to the left. And then you have to go up or down. In this case, we don't have to go up or down at all. So we do 0 movements up or down. Again, that's your x and your y value. If we do C, we look and we try to locate our point C. It's over here. The first thing we do is go to the right. 1, 2, 3, 4, 5, 6. So we go 6 to the right so that we're directly above it. The 6 is your x value. And then you go down to point C. So you go 1, 2, 3 down. That's -3 down. So whenever you're going down on a graph, it's negative. So left is negative. And down is negative. Alright, you can try to pause this and do D and O on your own. I'll put in the answers in here so you can check to see if you did it right. O is going to be 0 because we didn't have to go left or right any, and -3 because we had to go down 3. And O, we didn't have to move at all to the left or right, so it's 0. And we didn't have to move at all up or down, so it's 0. These points are all the points on the graph. Alright. Question 2. I guess D. Write the coordinates of the points in the second coordinate. So that's a term we need to remember. It's called the second coordinate. Whenever you have a graph like this, you'll notice that they're broken up by a y-axis and an x-axis. And when we break that up, we have 4 distinct quadrants. We have this one, we have this one, we have this one, and we have this one. Now those coordinates all have special names. So we use Greek letters to describe them. Sorry, erase this off. And we always start in the top right-hand corner. So this very top right-hand corner one, we call it quadrant 1, and we represent that with an I. We then go counterclockwise, so we move to the left and we go to quadrant 2. We then go to the bottom and we find quadrant 3, and we move to the right and we find quadrant IV, which means 4. So that's the naming of all the quadrants. The question is, write the coordinates of the points in the second quadrant. So if you're looking at the second quadrant, there's only one point in that quadrant, and it's point E. So they want to know, where is E? Well, it was 2 to the left, so -2, and then it was 3 up. So your point E was at -2, 3. A good question here is usually, what about point B? Is point B in quadrant 2? If a point is touching the line of one of your axes, it's not considered to be in any coordinate. So we just say point B is on the x-axis. It would not count as in quadrant 2. All right, C. Write the coordinates of points in quadrant 3. I want you to pause the video, see if you can answer it, and then check. So if we look over in quadrant 3, we find that only F is down there. And the point for F was 4 to the left, so -4. And then 3 down, so -3. And that is our point. Question D. Complete the following table using positive or negative. So, quadrant 1. When you're in quadrant 1, what are all the values in the x going to be? So if you're in quadrant 1, it means that you've moved to the right, which means that it's always going to be positive x values. If you're in quadrant 1, it means you've moved right and up, so that means you're also always positive. If you're in quadrant 2, you've gone to the left, so that's negative. But you're still going up, so it's positive. If you were in quadrant 3, you've gone left again, so you're negative. And you've gone down, and down is negative. Lastly, quadrant 4, we're now going to the right, so that's back to being positive. But we're still going down, so it's still a negative. That's good information to know, because if someone ever tells you there's a point in quadrant 3, you know the x and the y values both have to be negative. It's just a good way to be able to consider where things are on a plot, on a Cartesian plane. Alright, a little word problem to get us going. So, what we're going to do is we're going to create equations in this unit and learn how to graph them. This question talks about toothpicks. So, there are 3 toothpicks are used to form a triangle, as you can see here. 1, 2, 3. A second triangle is formed if you add 2 toothpicks. So we had our original 3 toothpicks there, and then we added 2 toothpicks, and we created a second triangle by adding only 2 more toothpicks. You could do this again, and you could add 2 more toothpicks, and you would get another triangle. So the question here is to draw the next diagrams in the pattern. Well, our next diagrams in the pattern would be simple. We would take what we already have, and we would add 2 more toothpicks to get 1 more triangle. The next pattern would be the same thing we just did, but we would add 2 more toothpicks. And you see that for every 2 toothpicks we add, we're gaining 1 triangle. So part B says complete the table relating the number of toothpicks P to the number of triangles T. They've already filled the first one for you. They said if you want one triangle, you need 3 toothpicks. If we look at our diagram, how many toothpicks do we need for how many toothpicks do we need for 2 triangles? Well, we would need 5 toothpicks. How many toothpicks would we need if we wanted 3 triangles? Well, we would need 7 toothpicks. And you notice the pattern that you're just always increasing the number of toothpicks by 2. That's not a coincidence. Part C, represent the data from the table of values on the grid. What we just created in part B, this is called a table of values. They want you to take that table of values and put it onto your grid. And notice that they labeled P and T instead of X and Y. And that's quite common that they'll use different letters to represent X and Y, but they still mean the same thing. So, our very first thing we want to plot is we had 1 triangle, so we went 1 to the right. We needed 3 toothpicks, so we go 1, 2, 3. And we create a dot right there. And that dot will show us our first point on our table of values. Our second one that we had was 2 triangles, so now 1, 2, and then it took 5 toothpicks. So 1, 2, 3, 4, 5. That's where we draw our next point. Again, we're going to do that for the next point, and the next point, and the next point. I want you to try those on your own. Pause the video, see if you get the same points as me. So hopefully you've unpaused the video now, and you see that I've drawn in all 5 of my points, and they actually form a nice little line. But we haven't connected the dots. We've just put the dots on the plot. These dots each represent how many toothpicks it would take to create a triangle. Question D. Explain why it does not make sense to join the points in a straight line. So when you join points on a graph, it means something specific. If you were to join those points, it means anywhere on the line that you created, that would be a new triangle. And that really wouldn't make sense. So for instance, if we drew a line in between these first 2 dots, what that's saying is it's saying that you would have 1.5 triangles if you had 3.4 toothpicks. And that doesn't make sense because you either have a triangle or you don't have a triangle. It's either you got a full triangle, you don't got a full triangle. Even if I add 1 more toothpick, I don't have another triangle, so it doesn't make sense that I would have that as a point on here. Instead, what we do is we leave the data as points. I'm going to move this box, and you'll see we have a nice little explanation for it up here. So the number of triangles formed only happens at certain numbers. You cannot have partial triangles built. That's why we have dots and not a connected line. Question E. Describe in words the relationship between the number of toothpicks and the number of triangles. Well, if we were to look at our data, we would know that once you have 3 toothpicks, you have 1 triangle. But for every 2 toothpicks you add, you get 1 more triangle. And I've put that in words nicely there for you. Just describing the relationship of 2 more toothpicks equals 1 more triangle. Question F. Write an equation that could be used to determine the number of toothpicks if we know the number of triangles. So, the number of toothpicks is P and it's going to be equal to the number of triangles sorry there, just had a little bit of something stuck in my throat, had to cough. So if we wanted to write an equation here that would represent the number of toothpicks if we knew the number of triangles. We want toothpicks all the way over here by itself, and toothpicks is represented with P, and it's going to be equal to the number of triangles, but we always got a triangle after we multiply by 2. Right? So that 2 represents every 2 more toothpicks I was adding on. Now the problem was, if we left it like this right now, that wouldn't make sense, because the number of toothpicks wouldn't equal 2 times the number of triangles, because the very first triangle, you needed 1 extra toothpick. Sorry. That is an equation that represents the number of toothpicks when we know the number of triangles. And if you don't believe it, try it. So if you had 1 triangle, instead of T, write the number 1, and you would realize that 2 times 1 is 2, and then plus 1 more is 3 toothpicks makes 1 triangle. We're going to do a lot more work with this, so if this is confusing you, that's okay. It's pretty new, it's pretty fresh. So G. Use the equation above to determine the number of toothpicks if there's 27 triangles. So they're saying if you know you have 27 triangles, how many toothpicks should you have? If you look up at your equation, what they've done is they've told you what T is equal to. They're saying T is equal to 27. So you're going to change T to be 27. You have P equals 2. And whenever we replace a letter with a number, we put brackets. So bracket 27 and plus 1. We've taken our equation, we've changed T to be 27 because they told us how many triangles we had, and then we used brackets. Those brackets mean multiply. So if you put this thing in your calculator exactly like that, 2 bracket 27 bracket plus 1, that will tell you how many toothpicks it takes to make 27 triangles. The answer is 55 toothpicks. Alright, H. Now H is going to be the other way around, where they've told you how many toothpicks you have, and they want you to try to figure out how many triangles you would get. In this case, instead of telling you T, they've told you P. So we need to change P with 83. So you have 83 equals 2T plus 1. Now we need to remember some of our algebra skills. If you want to figure out the number of toothpicks, that means you need to get the number T all by itself. To get T by itself, we do what I call reverse bedmass. So we're going to get rid of any additions or subtractions first. So we need to get rid of this plus 1. To do that, we minus 1 from both sides. And we get 82 equals 2T. We continue our way through reverse bedmass, and we try to get rid of any divisions or multiplications that are happening to the letter that we want. In this case, we have a multiplication of times 2, so we need to divide both sides by 2. And we get that T would equal 41, meaning that if you had 83 toothpicks, you would have 41 triangles. And you can imagine if you went back to the very beginning and you tried to draw out all those diagrams, that would be very difficult. So it's nice to have these formulas. That makes it a little bit easier on us. Alright, we discussed something earlier. We discussed if you should connect the dots on something or not. If you're connecting the dots on a graph, that's called a continuous graph. It's continually happening. It's growing together. There's a point at every single number. If you're not gonna do it, it's called discrete. So discrete is dots, continuous is a line. Discrete data is things that doesn't make sense to connect them. So if we look at our example down here, it says classify each of the following variables as discrete or continuous. Question A, the time taken to complete a 100-meter sprint. So if you imagine all the possible times you could get for completing a 100-meter sprint, you realize that that would make sense to connect it as a line because you could really end up on any single point in time. So this would be continuous. For B, they talk about your shoe size. And your shoe size, it would make sense to only go up one level at a time. It's like tiered off levels. I'm never going to have my shoe size be 10.123. My shoe size is going to be either 10, maybe 10 and a half, maybe 11, but it's never going to be anything in between those things. And when that happens, we call it discrete. So that's discrete data. For C, the number of students who pass Math 10C, again, I'm either going to have 30 kids pass Math 10C, we're going to have 31 students pass Math 10C, but we're never going to have 30.75 students pass Math 10C. It's not possible. So you're going up in levels, in tiers, and there's nothing in between those levels. So that would be discrete data. For D, we're talking about the height of a student. The height of a student obviously doesn't just happen overnight. You don't just go from 5'10" to 6 foot. It slowly happens. You're always growing slowly. So this would be continuous. Your height doesn't magically just become 6'1". At some point you were 6'0.5" of an inch. At some point you were 6'0.6" of an inch, and you slowly grew all the way up to it. All right, we're almost done. We're going to talk about relationships between two quantities. This page shows a whole bunch of different ways that we can compare two things. So previously we talked about toothpicks and triangles, and we represented it using a table of values. We also represented it using a graph, but there's many other things you can do. So here's an example of a table of values. These are called ordered pairs. This is a graph right here. Down here is a mapping diagram, so that's a different way that you could represent things. And the very last one on the bottom here, that's an equation which represents things. These are all different ways of representing relations. You've seen all of these before, except a mapping diagram might be kind of new to you. So mapping diagrams, the way they work is they say you take a point on the left because you notice that the arrows all started in here. The arrows don't point in here. The arrows then take you somewhere. So for instance, if I had the point 20, and I said my S is 20, that would tell me that my C value would then be 10. And that's how a mapping diagram works. You find where the arrow starts, and then you let it take you where you want. The point 70, if it was my S value, would take me up here to 7.5 for my C value. It's called a mapping diagram. Everything else you've seen before shouldn't be too surprising. This is a good little notes page for you. The equation below illustrates a relationship between two variables, C and S. So this is a way of representing the relationship between two things using letters and an equation. In this example, the cost of driving a car depends on the speed of the car. So C means cost, and S is your speed. When you have something set up like this, the number that's off on the left is called the dependent variable, and S is called the independent variable. Because if you change S, so maybe S was 1, that's going to have a major effect on C. So we call S the independent and C the dependent. When representing a relation, we often regard the values of the independent variables as inputs and the dependent variables as output. So the independent variable is the input, so that would be C as the input. And the the independent variable is the input, and the independent variable was S. The dependent variable is the output, which is C. Remember, we just described them as dependent and independent above. Finally, the input value makes up something called the domain. And the output values make up something called the range. So in this case, our input was S. So S would make up the domain, and C would make up the range because it was the output variable. Below here, you'll see that they've changed S and C to become X and Y because when we graph things, we're always talking about X and Y values. So you'll often see us change things to X's and Y's. And you see they've labeled Y as the dependent variable, which means it's the output, which means it's the second coordinate in an ordered pair, and it's on the vertical axis if you were graphing. They've given you all this information right up front. The same thing over here, they tell you that that's the independent variable, which means it must be the input. It's also the first coordinate on the ordered pair, because X always comes first, and it's graphed on the horizontal axis. This is a good little notes page to reference whenever you see words like independent or output or domain. Consider the relation described by the equation. Complete the first 5 rows of the following table of values, which shows some of the possible input values. So we have a graph here, and they've given you a table of values with some possible inputs. They haven't said that's all the inputs, they're saying that's just some of the inputs. What we want to do is calculate the output for each given input. To do that, what we do is we take our original form, so y equals 2x minus 5, and we change x to be what the input is, because x is the input. So our first one would be y equals 2, and instead of x, we put what our input is, -2 minus 5. You punch that in your calculator and you get -9. So your output would be -9. As an ordered pair, we always write it x comma y, so it's -2 comma -9. Let's try that again. So they've given us an input of -1, meaning that instead of writing x, we write -1. Everything else stays the same. In your calculator, you then put that portion in. So 2 times -1, because that's what the brackets mean, and then minus 5 gives you -7. So -7 is my output, meaning that -1 comma -7 is my ordered pair. Go ahead, try the next 3 on your own. Pause it if you need to, and compare your answers to me. Alright, hopefully you've paused that and unpaused it. You're checking your answers and you're the same as me. Some things I do want to make a point of. You'll notice that the y values, they're all increasing by 2. Every time we go up 1 level in the input, we seem to be jumping 2 in the output. And that's not a coincidence because you notice there's a 2 right there. We'll get more into that later, but it's just notice that it's not a coincidence. Also notice that when your input was 0, you got an output of -5, and that's also not a coincidence that -5 is the thing in the equation that wasn't next to the x. You don't really need to know much about those things. It's just a little bit of tidbit of information that we'll use in a week. It's good, cool things to notice. But for now, all I want you to focus on learning is that when you're given an input, you can find an output. When you know your x, you can find your y. Last question. So we're going to do this and then we're done. We're going to plot the ordered pairs that we found on the previous slide on the grid. I've put them right down here. So I've copied the grid right down there. We are going to graph all of those dots. So your input was -2, your output was 9, meaning I go 2 over and then 9 down for that point right there. That's your first one. Your second point is going to be 1 over and then 7 down. And then you're going to have 0 and 5. And then you're going to have 1 and -3. And you're going to have 2 and -1. And you notice that you've created 5 dots that are all in a nice line. If that was fast for you, take your time, pause the video, graph those things as your own, make sure that mine line up with yours. Question B, connect the points on the grid and extend the line in both directions. So you'll see these lines, these grid points all make a beautiful straight line. They want you to draw a line right through it. Use a measuring stick or something flat. Something that works really good is the back of your calculator. Works as a good straight edge. I want you to connect all of those things. And you should get a nice straight line that goes right through all the points like mine does. And I want you to draw little arrows on the end of your line. Because those arrows mean that line would go forever if the graph was just a little bit bigger. Having that line will help us figure some things out. So for instance, if we look at question C, it says use the graph to determine the value of y when x is 6. To use the graph to figure something out, what we need to do is we need to go and find out where x is equal to 6. Well, x is equal to 6 right here. That's where x is 6. I've drawn a big red dot where x is 6. The next thing we need to do is we need to figure out what y value would make it so that we moved up or down and landed on that line. And you notice if we wanted to go from this big red dot and land on the line, we would have to go up. 1, 2, 3, 4, 5, 6, 7. We would have to go up 7, meaning that a y value of 7 would get us to our line. Meaning that if your input was 6, your output would be 7 for that graph. D, use the equation to determine the value of y when x is 6 and verify the answer. So now instead of using the graph, we're going to use the equation. And remember the equation was y equals, it was 2x minus 5. They've given you x equals 6, so that is your input. So we have y equals 2, and then times 6 minus 5. If you put that in your calculator, you'll get that y equals 7, which is exactly the same as what we said when we looked at our graph. So by knowing how to look and analyze a graph, you can actually skip having to do mathematical work like this. E, use the graph to determine the value of x when y equals 3. So it's the same thing now, except we're going to work in reverse. And we're going to figure out where y is 3. So y is 3 up here. 1, 2, 3. And instead of moving up or down, we need to move left or right because we're looking for an x value. And how far right would we have to move to land on our graph? Well, we would have to move 1, 2, 3, 4 spots to the right to be able to land on our graph, meaning that x would equal 4 if y equaled 3. For F, complete the following statement. The relation is called a blank because the graph of the relation is a straight line. So anytime you have a graph and it creates a straight line like we have there, we call it a linear relation, which is why this unit we're in is called relations and functions, and we always work with linear relations. Okay, that is the end of this lesson. I hope that you are understanding what's happening and that you can ask questions and practice.